Okay, and finally, for this chapter anyway, the one other reason that we have to look at for deviation from ideal gas behavior has to do with intermolecular forces. And this is because, as I said before, if you cool down a gas enough, a gas will start to condense into a liquid. And liquids don't behave like gases for the most part. And so that causes a pretty serious deviation from ideal gas behavior. That is, and it's not just when the gas is actually in the process of condensing into a liquid. Actually, it starts deviating significantly from ideal behavior while it's still a gas, but as the particles are getting close enough and just starting to cling to each other, that's when it really starts deviating from ideal behavior. And what happens here is the pressure will be lower than what's predicted by the ideal gas law. Okay, so you end up with a lower pressure. And there's a diagram of that happening to a gas as you cool it down on page 215 also. Even then, again, you'll notice that the deviation from the ideal gas law within reasonable temperature range is not all that big, but it's big enough to be considered significant by scientific standards. At low temperatures, what happens and what causes gases to deviate from ideal behavior is that the kinetic energy will be low at low temperatures, and the particles are not moving very fast. They collide with less energy. And they move apart more slowly. And that means that they may be in the vicinity of each other long enough for intermolecular attractions to develop. And that's because there are, as we'll go over when we get to the chapter on liquids and solids, because intermolecular attractions are what make liquids and solids, as opposed to gases. If there were no intermolecular attractions, everything would be a gas. And so, as we'll discuss the types of intermolecular attractions when we get to the chapter on liquids and solids, but suffice it to say for now, that a lot of these intermolecular attractions that can cause molecules to sort of stick to each other and become liquids or even solids operate over a very short range. And they require a certain amount of time because the attractions tend to be weak for any one part of a molecule. So they really kind of often require an entire molecule to stay very close to another molecule for a certain period of time before those intermolecular attractions can actually cause the molecules to stick together. Yes, so intermolecular attractions are often weak and often operate only over a very short range. And that's why the particles have to be near each other and have to stay near each other for a certain period of time before there's any. Okay, where were we before we were so rudely interrupted? The particles will move apart more slowly. That may be time for intermolecular attractions to develop. And the book uses the example of billiard balls with something sticky on the outside of them. So yeah, maybe maybe you rub the maple syrup over the outside of your billiard balls or something, and then you try to play pool with them. And you'll notice that the billiard balls don't exactly bounce off each other the way they normally do. They stick together a little bit from time to time, and sometimes they actually do stick together and they don't come apart. And so that's the kind of situation we'd be dealing with gas particles at lower temperatures. There is because at lower temperatures we have slower movement. That means that there are fewer collisions per unit of time. And those that do occur are lower in energy. And that results in a lowering of the pressure compared to what you would expect it to be based on the ideal gas law calculations. In the end, the particles just spend more time interacting with each other and less time colliding with the walls. So they're basically they're interacting with each other more often and colliding with the walls less often. Van der Waals is the same guy who investigated pressure-related deviations from the ideal gas law, or sorry, volume of the particles related deviations. And so now we're going to look at his correction for intermolecular forces. And so Van der Waals' correction of the ideal gas law says that the pressure is equal to nRT over V. This is the ideal gas law right here, but he added in an extra factor to correct for the existence of intermolecular attractions under certain circumstances, and that would be A times N over V squared. Okay, so out of this, A is a constant depending on the gas. And that was in that table with the van der Waals B constants on page 215, I believe. And N is number of moles, as it usually is in the ideal gas law. And V is the volume of the gas in liters. And you can actually condense these terms together and rearrange it, and you get P plus A times N over V squared equals nRT over V. And so this, normally it's P equals nRT over V. That's the ideal gas law. But this is the modified pressure for real gases, which equals nRT over V. And you can combine that together with the correction for volume. And you get the total overall van der Waals equation, which is P plus A times N over V squared times V minus NB equals nRT. And so you notice normally the ideal gas law is written as PV equals nRT. Well, here we have P, only it's P for real gases. And here we have V, only it's V for real gases, not ideal gases. So PV equals nRT. So it's essentially the same setup as we had for the ideal gases, only it works for real gases. So the first term is the corrected pressure. And the second term is the corrected volume. The first term was corrected for intermolecular forces, and the second term was corrected for particle volume. And so this can be used for calculating the properties of gases outside the ranges of temperature and pressure where ideal behavior would be expected. So these would be, again, conditions of relatively low temperature and or high pressure compared to everyday conditions. Sorry, not relatively low temperature and or high pressure. Because again, it's the conditions that bring molecules together that would cause deviation from ideal behavior. So high pressure or low temperature, because low temperature generally means condensation, or moving in that direction of condensation anyway. So that is actually the end of chapter 5, the gas laws for real gases. We've only got about 15 minutes left in this video, and we're still well ahead of schedule. So I think I will wait until the next lecture to begin the next chapter, which will be chapter, what is it? 11. So chapter 11 comes next, and chapter 11 is the one where we talk about solids and liquids and intermolecular forces of attraction in more detail. So some of this stuff that we've been talking about here in this chapter won't really be covered in detail until the next chapter. And that's because, again, intermolecular attractions are something gases don't have, but they're something that liquids and solids do have. Okay, so until next time, goodbye.